Buenas noches. So here we are. The sun radiating light towards the moon that is in between the sun and the earth. And during this eclipse, as photons travel and take 8 minutes and 20 seconds to get to the moon, the shadow, the sweet spot on planet Earth, finds itself in the moon's shadow. Photons have been travelling for 8 minutes and 20 seconds, and the sun is still in a direct line, directly behind the moon. How can that be? Because if photons were taking 8 minutes and 20 seconds to hit the moon, which then casts the shadow, planet Earth, as the photons are travelling, carries on turning, doesn't it, for 8 minutes and 20 seconds. That's a total of 2.08 degrees on its axis. So photons leave the sun, 8 minutes and 20 seconds later, they reach there. Photons leave the sun, Earth spins for 8 minutes and 20 seconds, which is the equivalent of 2.08 degrees on its axis. So when the photons finally get to the moon, and then poof, we get the shadow, the sweet spot, why is the sun directly behind the moon? It cannot be there unless the sun is radiating absolute light, and it obviously is, okay? So obvious it hurts. It's a water bottle, it's freezing. Now, what is a photon? What is a photon?
Can you explain what a photon is at several levels of difficulty, i.e. to a child, a teenager and a grad student? So if I had one of each in front of you.
No, clean lady.
What's a photon, Professor Copeland? To a child first.
So you see the light that's coming from that, shining from there, and it's coming into your eyes. That light is made up of photons, small little packets that are coming down to us all the time. So that's a photon is just allows that light to come down to you. It's made up of lots of little packets.
A photon to a child, it's like a little ball of light, I would say. Tiny, tiny, tiny little ball of light, okay?
Oh, that's cute. You've got a teenager now.
A particle of light. I would say that's the difference. It's a particle of light.
To a teenager, they've probably learnt a little bit about quantum mechanics. They might have just beginning to do it at school. So for a teenager, what I can tell you is that if I shine a beam of radiation into a surface of a material, and then what I can do is that atom that it's shining into is made up of energy levels. And the electrons in those energy levels, they can jump up. And when they jump up the level, they've gained energy. And we all know teenagers are very lazy. They want to be in the lowest energy possible. So the electrons drop back down. And in dropping down, that energy...
Are we talking about teenagers or photons?
That's been absorbed is emitted. And it's emitted as a package. And that package is the photon. That's precisely the photon. And depending upon how big that energy gap is, that tells you the wavelength of the photon. So it determines its colour. So it tells you whether it's yellow or it's red or it's green, depending upon that. And that is called the photoelectric effect, and that is what Einstein got his Nobel.
1921. And in 17 or 18 or 19, we had people win the Nobel Prize for working out that the local universe is not real, of all things. So, you know, how much weight do you give these things?
Prize for, not for relativity. And for a graduate student, okay, well, the idea of the photon is there. For a graduate student, I represent the photon through what's called a wave function.
Oh.
And it's a solution to Schrodinger's equation, for example. And that photon has certain properties associated with it. It's got a size where the wave function peaks, That tells you where it's most likely to be, and as it drops down, that's where it's not going to be anymore. But it's also got a spin, and it's got an internal spin associated with it. It's quantum numbers, so it's got this size represented by the wave function and the probability of it being somewhere given by basically the wave function squared. But the spin is what defines it as being the photon, and it's got an integer spin for a photon, whereas a fermion, the electron, has a half integer spin. The photon is a boson and it has an integer spin.
Well,
Do you get that? So if you're ever out and about and you see little particles spinning full turn at integer, you know it's a photon. Now, if you catch it out of the corner of your eye, just doing half spins, you've got yourself an electron, or what is it, a fermion or something, which from the family fermion, but it's an electron. And then of course the photon, whole spins, baby.
the quantum of light. That's what it is. It's literally the quanta. Every particle, every field has fluctuations, quantum fluctuations. There's the quanta associated with them. In the case of a photon, it's the quanta of the electromagnetic field. Analytic continuation of things like black holes.
There you go. So, the photon for dummies. The only thing is, I just find it's a bit strange that during a solar eclipse, there's really not too much room to move on this one, I'm afraid. We take all logical answers on board and obviously have a good look at them, but to this day, we still haven't had a logical answer for why the sun is directly behind the moon during a solar eclipse. The only way possible for this to be happening is if that sun right there is radiating absolute light. See? Not that kind of light, but that kind of light. I believe it's about common sense. Because it is about common sense. What's that? Nothing. It is about common sense, okay? It really is. It's not complicated. Very confronting, I do get that, but it is what it is. The moon, the sun, and the moon's shadow on planet Earth, very difficult to mistake them for anything other than what they really are. All right? Now, I know I keep hammering this over and over, but the actual age of the universe and the stars in the night sky, this is what is at stake. And it's obviously wrong. Okay, laters.